If you finish early, then you guys can start to send me your chat, or you can send me your answers in chat, and then we can I can see kind of where you guys are coming in. Let's see. Does that work better? Can you guys see that now? All right, you got about a minute left.
NIF.
All right, so we're coming up on it. About 10 more seconds. All right. So what'd you guys get for the first question? What'd you get for question number 14? All right, so we got a lot of people thinking it's D for 14. Let's see. All right, so when we're looking at this, right, and it's talking about boiling point, okay? Boiling point should always bring a topic up to mind, right? So what topic should always come to your mind when you guys think about boiling point? Intermolecular forces, right, is kind of what we're looking for. Now, size and stuff is also related to that, but intermolecular forces is going to be a big part of it, right? And that's because intermolecular forces are what's holding the molecules together, right? So let's say that we have a molecule, it looks like this, and there's a second molecule over here. The intermolecular forces are the attraction that those molecules feel between each other. Right? The force that's connecting those atoms inside of those molecules, those are called intramolecular forces. And those are things like our covalent bonds, ionic bonds, and metallic bonds. So our intermolecular forces, those are things that are holding the molecules together. And so what type of force do all molecules have as long as they have electrons? What type of intermolecular force do they all have? So they all have London dispersion forces. Now, sometimes I think dispersion forces seems confusing because they don't actually disperse your molecules. Dispersion forces are still holding them together. So I just like to call them London forces because I feel like it's not as confusing in your mind about what they're doing, right? So London forces are the ones that are holding them together, right? What else? What other type of intermolecular forces are there?
Ion dipole.
So we have ion dipole.
Dipole, hydrogen.
Hydrogen what? What's
Bonding.
the hydrogen one? Sorry, what was that, Chris?
Bonding.
And then we have the last one, which is hydrogen bonding.
Ion.
Now, ion is actually an ionic bond, right? So sometimes that's holding our ions together, but it's less of an intermolecular force because when you have two ions, you don't really have any molecules there, right? But that is part of it as well. And so if you wanted to think about it, ion would kind of go all the way down here, and then that would be the same as kind of like our ionic bonds. So the reason why this should come up when you guys hear things like boiling point, melting point, freezing point, all of those things is because our states are how close those molecules are to each other. So when they're solids, then they feel strong intermolecular forces between each other. When they're liquids, they feel some intermolecular forces between each other. It's enough that they stay close to each other, but not so strong that they're locked into place so they can't move around at all. And then when they're gases, they feel very few intermolecular forces to each other. It doesn't mean that they don't feel them as they're going by each other, but it's like they're moving so fast that it's easy for them to break away from each other. So if you wanted to imagine it, it's kind of like someone grabbing you, right? If you were to walk, someone could grab you and could kind of hold on. If you're jogging, someone could grab you and it could slow you down a little bit, but you could break free. And if you're running really fast, it's a lot harder for them to grab you with that same speed because you're, as a particle, are moving around so quickly, right? And so that's kind of this idea of these other molecules is they're trying to like reach out and attract the attention of that other molecule. So when you're a solid and you have a strong attraction, then these strong intermolecular forces there. So it's asking us, ammonia has a higher boiling point, then it's heavier comparisons of pH 3 or arsenic hydride. And so they want to know why. Why is that? Okay. And so we know that it has to deal with their intermolecular forces here.
Hydrogen bonding.
Well, so we're going to get there, but we know that it has to deal with their intermolecular forces. Right? Now, if we are a higher boiling point, is that harder to break apart or easier to break apart?
Harder.
Harder, right? It's why we had to put in more energy in order to make that occur. So a higher boiling point is stronger intermolecular forces. The same thing for a freezing point. Right? The lower your freezing point is, the stronger your intermolecular forces, because you were able to turn to a solid much easier. Or sorry, opposite way. So the higher your boiling point, the higher your melting point, the stronger your intermolecular forces are, because you're holding on to each other a lot more. Now, from there, we know that NH3 is higher than our pH3 and our ASH3. All right? Now, in order for us to answer whether they have dipole-dipole or hydrogen bonds, what do we need? What do we have to have for them?
Their Lewis structure.
We have to have Lewis structures. Now, as a quick check, we can see if just our London forces is enough to answer the question, because we don't need a Lewis structure for our London forces. Right? And so for London forces, how do they trend? What makes London forces stronger?
Is it the smaller the radius of the atom?
The bigger the mass.
So what's causing London forces? Can someone describe what causes London forces?
They increase with molar mass. So larger.
They do increase with molar mass. And so it's
Stronger-
not about their radius.
Stronger London forces are more likely to be solid.
So that's because they have stronger intermolecular forces. But what are London forces? What physical thing causes London forces?
Is it like the opposite charge of the nucleus?
So if it was dipoles, then you would have to be polar for it to be there, right? If it was the opposite charge of your ions, then they would all be ion, right? But it has to deal with this attraction between your electrons and your nucleus, right? But it's not even about your electrons and your nucleus. It's really about your electrons and the electrons of the atom next to you or the molecule next to you. Because what is it about electrons? What are the electrons doing inside of our molecule?
They move apart.
They move around, right? So if you had a circle and you had 12 electrons in there, right? Normally, your electrons would like to spread themselves out evenly through this whole thing. Right? So we get them all evenly spread out. But as they're moving, there could be a moment where those two electrons might have moved over to this side over here. When we look at this circle with its electrons, are those electrons evenly spread out now?
No.
No, right? Because one side has more electrons than the other, right? If we were to chop this in half, this side to our right has way more electrons than the side to our left. And so if we have more electrons there, what happens to our charge?
It goes up. Add
Right.
addition. I mean, sorry. I don't know.
So if there's more electrons somewhere, when you say it goes up, what does it become more of?
Positive.
So what charge are electrons?
It's the opposite. It's not positive. It's slightly negative. It's what
Slightly
we call
negative.
It's what we call a sigma minus.
Right? And so it becomes more negative because electrons are negative. And so sometimes this is always the problem that you see with electrons is we think when there's more of them, then it should be becoming greater, so it should be more positive, right? But we have to remember electrons are negatively charged. So they're becoming slightly negative on that side, and this side becomes slightly positive. Now, if this circle became slightly positive, then the molecule next to it is going to pick up on that. And because it's going to pick up on that, then this side is going to become slightly negative because the electrons are going to get attracted to that partial positive. And on the other side, it become partially positive. And so that's how London forces work between molecules, right? It's this movement of electrons. So is this a temporary situation or is this a permanent situation?
Temporary.
Very good. It's a temporary situation because the next moment, those electrons might travel back. And now even more of them might travel that way. And now everything could flip. And this could become negative now. This one would have to become positive. This one would have to become negative, right? This one would become positive. And so they can move around and they're ever changing. But there's always this flux of electrons moving around.
So Professor Lau,
Mhm.
I had indicated it's a dipole. Actually, I should have said transient dipole.
Right? And so it is. It is because there's this partial positive, partial negative
Partial
charge
negative.
as they move around. And so this part is temporary. And so the reason why molar mass matters to us is that the more electrons you have, the bigger these swings can be. And secondly, the larger your molecule is, the easier the orbitals are to polarize, and then the easier it is to see this as well, right? And so we just try to sum that all up with molar mass. So between our three options, NH3, PH3, and arsenic H3, who has the strongest London forces? Right? So ASH3 should have the strongest London forces because it's got the highest molar mass. Now, that didn't help us. That doesn't explain why ammonia has a higher boiling point than it. So we know that London forces isn't the culprit. That's not the reason for it. So now we still have to go back and we still have to do our Lewis structures. All right. So we have our three Lewis structures there. And so why do we care about Lewis structures? So we care about them because we do want to know about polarity. And which of these is tied to polarity? Which intermolecular force is tied to polarity? Dipole and what?
Dipole.
Dipole and dipole, right? So dipole is about polarity. And so if we don't know their three-dimensional shapes, it's hard for us to know our polarity, right? And so all three of these molecules, what molecular geometry are they going to take on?
Like a planar.
All right. So how many electron groups does it have?
Oh, 4.
4. Right? And that's because it's 3 atoms and 1 lone pair. All right. So the base shape should be what?
Trigonal.
Or, sorry. So our electron geometry
Trigonal planar.
should be not trigonal planar because trigonal planar only has 3 options.
Tetra.
Be tetrahedral. And now that we have our electron geometry, now we can look at our molecular geometry. And so our molecular geometry, right, we basically have our central atom. We have 1 up, we have 1 down, 1 coming forward, 1 going back. And so if you wanted to, you can imagine all of the lone pairs up on top, H is all down below. And so you guys are right, they're all going to be trigonal pyramidal. All right. So the all-trigonal pyramidal, that still doesn't tell us polarity, but it gives us a basic idea of it. And then we would have to look and we would have to compare their bond dipoles to find out if there's polarity. And so for ammonia, they all go from hydrogen to nitrogen. For pH 3, they also go from hydrogen to phosphorus, but they're smaller. And then for ASH3, they go the same thing, hydrogen to arsenic, but they're also smaller as well. So you guys were right that they're all polar. So if they're all polar, what kind of force do they have? Or sorry, if they're all polar, what intermolecular force do they have?
Dipole, dipole.
Dipole, dipole. So we do know that. Now, how can we tell if one dipole, dipole is going to be stronger than another? So our electronegativity is going to give us our bond dipoles, and we could kind of look at that to look at the size of our arrows. So that's one way to do it. Right? But that can be really hard to do. And that's because your bond angles can be different. And so to actually do the vector math to find out what your new dipole would be, the strength of it going in that direction can be really hard to do. And so instead, what might they provide if we wanted to compare the dipole-dipole intermolecular forces between different molecules? What kind of measurement would they give us if we wanted to compare that?
Celsius?
Not the Celsius.
Oh, is he talking about that?
So there's a term, right, where we talk about how polar a molecule is. So bond order has to deal with the individual bonds. And so that term comes directly from the word. So it's called a dipole moment. So a dipole moment is the strength of the dipole. The larger the dipole moment, the larger the dipole is. Right? And so this is something that they would have to measure. Right? If they just gave you these three molecules, it would be really hard for you to find out who's got stronger dipole-dipoles. Right? It's just a complicated thing. But they could give you the dipole moment, and you would be able to measure who's got stronger dipole-dipole forces. Right? The higher your dipole moment, what it's saying is the more polar your molecule is.
In the question, would they state which one has the highest dipole moment?
So they would just give you a value. So they might tell you that NH3 has a dipole moment of 3.6, 1.8, and 2.4, right? And then that's how you would get that information. So it wouldn't be something you would deduce. It's something that they would provide. And you would just need to know that the higher the dipole moment, then the more polar your molecule is. Does anyone have any questions on that part? So we know that London forces weren't our answer, and we know dipole-dipole seems too hard for us to judge based on the information they gave us, right? And so what other intermolecular force haven't we looked at that we might be able to tell for this molecule?
Oh, we know that hydrogen bonds can form between fluorine, nitrogen, and oxygen that are attached to hydrogens.
All right, so it's all hydrogen bonds. And so hydrogen bonding is like a very special dipole-dipole bond, right? And you're right. We need two things. We need a hydrogen atom, and it has to be directly connected to nitrogen, oxygen, or fluorine, right? Those three at the very top right of your periodic table. And so out of our three molecules, does any of them have a hydrogen bond?
NH3.
NH3, right? And so when we're looking at our answers, the first one is saying that NH3 is trigonopyramidal and polar, while the other ones are trigonoplanar. So we know that's not true. One is more acidic than the other. Well, that's not true. Especially because if you knew that ammonia, right, NH3 is a base, which is why the whole thing about Lewis acids, Bronsted-Lowry acids and bases had to be created, right, instead of Arrhenius, then we would know that. We know that it also doesn't have stronger London forces. And so the only option that it could be is its extensive hydrogen bonding. And so what I was told in high school, right, and sometimes I do think that it holds true when you're first learning this stuff. Whenever something really funky happens in terms of boiling points and melting points, and you're just really confused about why it is, one of the things to look at to explain it all the way is hydrogen bonding, right? Hydrogen bonding has such an impact on things that it is what bucks the trend for a lot of things, right? So NH3 we would think would have a really low boiling point, but it doesn't. And it doesn't because it happens to have these hydrogen bonds.
It's
Water,
like soluble or insoluble or not?
so sometimes it has to deal with soluble and insoluble, but soluble and insoluble has a lot more to deal with what you're trying to dissolve it into, right? And then the strength of those molecules. And so water is another example of something that has really high or really low boiling points in compared for its size, right? So it's got a really high boiling point, a really high melting point for being only 18 grams per mole, right? And so hydrogen bonding answers a lot of that type of stuff. Do you guys have any questions on those intermolecular forces?
Isn't it a bit better to like, I mean, it doesn't really matter in what way you list it, but I feel like FON is a better way of remembering it.
Definitely up to you, right? Whatever makes it the easiest for you to remember. The only advantage of NOF, right, is that that's how it shows up on your periodic table, so it's easy to find, but it doesn't really matter. So you can remember it either as NOF or FON. The only really important part, make sure that hydrogen is directly connected to them, right? If you have a carbon in the middle and it's got a hydrogen and it has a fluorine, that doesn't mean it has a hydrogen bond, right? It's only if that hydrogen's directly connected to that fluorine. Okay, then let's look at the next one. In which are the ionic solids ranked in order of increasing melting point? So what holds that together? When we're looking at ionic solids, what's holding an ionic solid together?
Is it the lattice?
The lattice is a part, but what force is holding it together? Very good, Anthony. It is the ionic bonds, right? So our ionic bonds is what's making up that lattice and what's holding it all together. And so you're right, when it's asking about who's got increasing melting point, we are also looking for who has the highest lattice energy. Because whoever's got the highest lattice energy, we have to put the most energy in there in order to break it and turn it into a liquid. Okay. So what two things matter for lattice energy or ionic bonds? What are the two things that we need to compare?
The charge and then also the atomic size.
The charge and the atomic radius. Right? And so the reason why they use radius instead of size is sometimes people get confused with size and weight, right? And so they choose your highest molar mass, but really you want your largest atomic radius, right? Volume. But both of those work, right? And so,
That's a quick question.
Mm-hmm.
So if we're talking about ions in ionic bonds, are they still atomic radius or do we use like ionic radius?
So you would still use, it would be better to use ionic radius. Right? The harder part is you don't necessarily know all of your ionic radii in comparison to each other, right?
Okay.
So what that means is we have a periodic table. So we can judge the atomic radius between sodium, lithium, potassium, right? We can put all of those in order. It's a little bit harder to do something like sodium plus and then barium 2 plus and our aluminum 3 plus. But really what we end up comparing them as is sodium, barium, and aluminum, and then kind of hoping that their trends hold true, right?
Right.
And so if they're all isoelectronic, we can compare those. When they're not isoelectronic, then we're kind of making some choices when we do those comparisons. But you're right, that in the end, we are kind of trying to look at their ionic radius. And so we want to keep that in mind, right? And so that would be something like sodium plus and magnesium 2 plus. Who has a smaller ionic radius?
Would it be magnesium 2 plus?
Right? It ends up being magnesium 2 plus because we have the same number of electrons and magnesium has more protons, right? And so you're right, ionic radius is probably a better term for it. It's just when we're looking, a lot of times we're doing the comparison with the atom radius. But either one, that's a good point.
Okay. I wasn't trying to make it overly confusing. Sorry.
No, it's okay. It was a good clarification, right? And so when we're looking at here, which one matters more right off the bat? Is it going to be our charge or is it going to be our radii? Which one do we normally want to start separating out?
It's the charge, right?
So generally we want to get our charge. Our charge has a big impact. And that's because 1 times a minus 1, right? This gives you an attractive force of -1. Whereas if this goes to a -2, that doubles in its impact, in its radius, right? If we get 2 and -2, we're 4 times as big, right? And so our charge normally is the one that drives it because it's less likely that our atom is going to be twice as big as the one before it. But sometimes that can happen, so it is something to be aware of. And so when we're looking at this, is higher charge going to give us a higher melting point or a lower melting point?
Higher.
Higher, right? And so we want everything with the higher charges over here on the right. And so for our options, we have KBr, NaCl, sodium fluoride, and MgO. This is a +1, -1, +1, -1, +1, -1, and MgO is a +2, -2. So for these, who should be our highest melting point?
Magnesium oxide.
Yeah.
All right. And so just with that, we've kind of narrowed it all down. But we should double check as well. So we'll just double check the rest of them. But right now we're looking at magnesium oxide. All right, we know that one's going to be the highest. Okay. So looking at these next ones, do we want a bigger size or a smaller size if we're looking for an increasing melting point?
The second largest.
So we want our radius to be going down, right? The smaller our radius, the stronger those attractive forces are, and then the higher that melting point is going to become. So we want to be going down in that one, right? So between potassium and sodium, who is bigger?
Potassium.
Potassium is lower, right? So potassium is going to be larger. And so between bromine and chlorine or fluorine, who's the largest? bromine. Right? So our biggest ionic bond or length of the ionic bond is going to be our KBr. And if we were to compare these as K plus, Na plus, minus, 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 it doesn't change the order that they're going to be rated as, right? So KBRs are our lowest. And then who's coming next? Is it NaCl or NaF?
NaCl.
NaCl. And then who's after that?
Yeah.
NaF. And so does that line up with our answer of A? Yeah. And so that's what we're kind of looking for. So for some of these type of things, right, especially for your ACS exam, it's okay to use some of those test taking strategies. It's kind of what I don't like about the all multiple choice ones, but it is one of those things that basically just by checking charge, you could have answered the whole question, right? Because once you got MgO in the correct place, you didn't even have to do the rest of it. You already knew that it was A. Right? If you have extra time, it's always nice to do that second part, and that way you can catch yourself if you made a mistake. But if not, then that is one way to kind of move you along. So if you're struggling with speed on this, then that's one way to kind of move that along. Does anyone have any questions on that? Okay. So I want to pull us back just to the main screen or like our Canvas page, because I want to talk to you guys kind of about what resources you have, just as you guys are starting to get ready for your exams and kind of what's going on. So I sent out an announcement this morning about what's kind of coming up for these next 2 weeks. Right? And so basically we have class today, which you guys are all here for, yay. On Wednesday, we'll also have online class again, right? So there's no in-person lab this week. Okay? The class on Wednesday, we'll do some more problem solving. We'll also do the online lab. And then I'm going to let you guys go an hour early so that way you guys can do the quiz, because I really want you guys to get your quiz number 9 done before Friday. So that way you guys can get some feedback on it, right? If you all wait till Friday night at midnight to get it turned in, then most of you don't get any feedback on how you did until Monday morning, right? So you want to make sure that you get those turned in so that way I can grade them and you guys can see how you're doing on that part, okay? And then next week, we have our ACS exam. That's going to be on Monday. And then on Wednesday, we'll have the final exam. And so I've made 2 pages for it that I'm working on, kind of getting set up for it with your ACS exam and some information about it. And then I'm going to be working on this final exam page, kind of like your materials, where it's at, what to bring, things like that.
So on December 9th is basically like our last day of class.
So December 9th is the last day of class, right? So that's going to be next Wednesday. After
Okay.
that, we're done.
Yay, thank you.
Now, on that, you want to make sure that you check your grades, right? So your grades are being updated. Exam number 3 is graded. It hasn't been curved. That should happen tonight. Once it's curved, they're going to you guys' grade books. But this week, you want to spend some time, make sure that there's no mistakes. So if there's a mistake for your Connect homeworks, any of your labs, you're not sure about your quizzes, right? This is the week to ask, because next week what will happen is you would take your final on Wednesday, I will grade it, and then grades have to be submitted by Friday, right? And once grades are submitted to CCC, it's a lot harder for me to change them. So if you have questions about your grades, if you think that there was a mistake, right, either on how things were graded or how they were input into the grade book, that's totally fine. Sometimes things do happen. Let me know, and you want to try to do it this week, because by next Wednesday, once your final comes in, I will grade them, and then it's just going to get finalized, right? So if you have questions or things that you want to get taken care of, that you want to take care of that. Okay. I do also have office hours this week, right? My link is down below. Now, it's good. Come early, come often, right? I'm also going to change my office hours. I won't have them on Thursday, but I will be available for that same hour on Friday instead. And so I'm just shifting them back because I know on Friday people seem to have a lot of questions. But you want to start asking those questions early, right? Today we already had a pretty busy office hours day, so that was good. So I encourage some of you that I've never seen in office hours but seem to have a lot of questions, that's a good time to come and get some of that clarified, especially if it's about things like, I'm not sure how my grades are, I don't know how to get into your grade scope, I'm confused about what's going on for the final exam or the ACS, right? Things like that, good thing to come and ask questions about. Do you guys have any questions on that?
Would you ever start office hours earlier tomorrow or no?
It's hard for me to start office hours earlier tomorrow because I teach until 12:35, right? And so that's why it starts at 1, so that way I can eat lunch.
Sorry, thank you.
The lowest score for your quiz in your lab, those will get dropped next week, right? So normally that's what I work on between Monday when you guys take the ACS exam and Wednesday when the final exam. That's when I'm working on going through and manually removing your last grade or your lowest quiz, your lowest lab, right? And so you want to make sure that if you have questions about your scores, you get them in before that. It's significantly easier for me to make adjustments before I start averaging your scores and replacing them.
Will you prefer that us come by your office hours, or is sending an email okay?
You can send an email, but if it's a complicated question, you probably want to come to office hours, right? So if it's like, hey, I didn't get a score for like experiment number 12, right? That's a fine one, send me an email, right? If you're like, on number 12, I put down this answer, you gave me half a credit, I think I should get full credit because of yada, 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 then maybe that's more we should have a discussion and then you should try to come to office hours. But at the very least, if you can't make office hours, then let's send me an email so at least we can be aware about what's going on, okay? All right. The other part is if you look at the module for this week, this week's modules will go through for the rest of the semester, right? So it's 15 and 16 down here. So today's meeting is that ACS exam review. We have Wednesday's meeting, which is going to be the final exam review. This is your quiz, so it's already live, so you guys can start taking your quiz score, or your chapter 12 quiz. And then there is an online lab. Now, I'm going to show you the ACS review page, just so that way you guys know what's on there. The slides that I'm getting all these multiple choice questions, that's the same pack from last Wednesday, right? So that's here. Later on today, we are going to work through a multi-step problem. And so you guys can download that as a PDF right over here. And then this is the same information from last week, the main topics that are on the ACS, the differences, and your resources for it. For your final exam, there is another review pack for that. So as you guys start getting ready for your final exam, so more of those practice problems, there's a study guide. That study guide is basically a chapter by chapter list of your different topics, right? So it talks about chapter 1, what are like the big things that you want to know and be able to do. Chapter 2, your big things, chapter 3, and so on. It doesn't necessarily include every possible detail, but it's supposed to give you guys the key concepts, the big topics. Do you guys have any questions on that? I've tried to pull some sample problems. So one of them is like this, where it's a whole bunch of multiple choice questions based on each chapter, kind of going all the way through to chapter 12, I believe. So this one you can also do if you're trying to prepare for your ACS exam. It's a lot of multiple choice questions. And so I've tried to put those together. I've also tried to make this exam review worksheet, which is a little bit more like the problem, the multi-part problems. Right, so it has you guys kind of doing a couple different things with the same type of information. And so that's kind of the idea behind them. So one of them is kind of a bunch of the multiple choice ones. The other one is more of those multi-part ones as you're going through them. So these are a good resource to start reviewing before Wednesday. So that way, if there's a topic or a problem that you want to see done, then that's what we can do on Wednesday, right? So you want to use that time. If you wait until Wednesday before you look at any of these type of work, then we're missing out on that opportunity to do a lot of that problem solving, right? And so if there's a topic that you want to, well, I would just recommend opening up that packet and taking a glance at that. Right? And then this precipitation reaction final review problem, that's the one from today. So we're going to do this one. So you guys will see those. Okay. And so there's that. Now, the last piece of information is going to be that for your final exam, you guys will get a note card. Let me see if I have the image. There we go. All right. So for your final exam, so this is the one on Wednesday, you guys will get one 3-inch by 5-inch note card. You guys can write on that front and back. If you don't have a note card, that's fine. You guys can take a piece of paper and you can cut it 3 inches by 5 inches. Now, these index cards, they are not the big ones, right? So the big ones are 4 by 6. Let me see if I have them. The 3-inch by 5 inches, the smaller ones, right? Now, those do have to have your name on them. So in that top right-hand corner, if you guys can put your name and your student ID on them, that would be great. They also need to be handwritten, right? Now, the reason why is a couple things. One is I feel like when people type them up and print them out, you guys fill a lot of information on there, but it doesn't seem to actually help you, right? Because you've made no decisions about what you include on there. You've kind of just trying to include everything, right? The second one is that the chance that there's been more cheating going on with my with the note cards seem to tie directly more into people that are copying and pasting answers from online and then having them printed out and putting them on, right? So I want them all to be handwritten. I just think it's part of the studying process. I understand that you might write big. That's okay. It just means that you have to make some choices about what you put in. You can write front and back on these note cards. That's totally fine. Just make sure your names and your student ID is there in that top right-hand corner on one of those sides. And then you turn these in with your exam, right? This was kind of how the equation sheet started. Was my first semester, I looked at what people were writing down, and then I tried to migrate what I thought was reasonable from their note cards onto the equation sheet. So you'll still get your equation sheet, but you guys will also get this note card, right? This is the final exam. So this is the one on Wednesday. This is not for the ACS exam, so that won't be for the Monday one. But I would say that as you guys are getting ready to study, making the note card is a good tool in that studying process, right? Because it makes you choose what's important information, what's not important information, what topics do you need support on, what topics do you not need support on, right? So I think it's a worthwhile thing to do. I would definitely recommend that you make one. I wouldn't necessarily recommend just asking someone to look at theirs and copying theirs down because it's not as useful, right? And the last thing is make sure that you guys are on time for your final exams, right? Once a final is turned in, then no more final exams get given out, right? So even if you guys have 2 hours and 30 minutes to finish your exam, if someone turns theirs in an hour and you show up an hour and 15 minutes late, then you just won't be able to do that exam and you get a 0 for it, right? So you want to make sure that you show up on time. So that way you guys can take care of that. And then on a whole different note, right? If you feel like you have a COVID exposure or if you're not feeling well, right? If you're showing any of those symptoms, then don't come, right? Let me know instead, and we will set up an alternative for you, right? What that might look like is you might get an incomplete for our course for this semester, and then we will arrange a different date for you to be able to come in and take your exams, right? So if you do have like a COVID concern, so let's say that someone near you tested positive and so you need a quarantine until your test results come back, that's totally fine. Don't come to class, right? Let me know, and then we will set up our alternative accommodations for you, okay? If you're feeling sick or anything like that, or if you have a fever, right, then also don't come. We can set up a different time for you to take yours, right? Your health is more important than our class. And so we will make sure that we can accommodate you in some way or another. Do you guys have any questions on that? And so if something does come up, if you have a health concern and things like that, just let me know and we can always talk about it, right? There are options out there. And so if you're not sure, let me know and we'll discuss it. Perfect. All right. So we have 2 things that we can do now. We can either, well, actually, sorry, there's one other part that I forgot to discuss for your online lab. So we'll go over this on Wednesday, but make sure that you guys can run this simulation. I just need to know about how much time we should be spending on it, right? If people can't run the simulation, we'll have to collect all the data together, which is fine. I don't mind collecting the data together. It just means that it's less time for us to do more practice problems, right? So if you guys can collect them, then we'll just keep it brief. If you guys can't collect the data, then we'll walk through it. It does require Flash to be able to play it. But other than that, it's a pretty straightforward one. You just need to choose your solvent, your solute, the amounts, and then you're measuring the boiling point or the freezing point, depending, right? So you can give that a shot. But if you have questions about that, just make sure you can open this page, that you see the simulation, that you guys can click on it. So that way we know, okay? And then there is a video. If you're not sure how it works, you can always click on this video. It brings up a like a user guide about how to change things, how to set it up. Okay. Okay. Now we have questions. So we're going to take a poll, right? And in your poll, what you guys can do is you can let me know if you would rather do the multi-part questions, so the worksheet, or we can do more multiple choice. So I'm going to run this in a second. I just need to make it. So multi-part. And you guys can let me know which of these you want to do. So let's go ahead and launch this. So you have 2 options. We can either do the worksheet or we can do the multiple choice.
I'm just kind of wondering, is so for these like practice problems on the ACS and like I guess just in general, is there like a what, like I guess kind of a in order like just a PDF or whatever of like just the practice exam? Like with all those sample problems?
Those sample problems are, that's where I'm pulling them from, is from that slide pack. And so there's the order that I've tried to coordinate them is, you can see there's like the 8 big topics. And so it talks about the big topic, what that covers, and then it has sample problems for that topic.
Yeah, okay. I'm just
Yeah.
wondering if there's like a website or something where you could like find
So if
basically
you,
just like the sample problems.
so if you want the sample problems, these I pulled from the ACS Olympiad, right? So that was that website that's linked at the bottom of the ACS, or sorry, of the ACS exam information. And so it's the one that goes through, basically they have like 20 years of exams for you guys.
Okay.
But that's where I pulled it from.
All right, thank you. What I think like I remember you saying that it wasn't like a perfect resource or something like.
And so you have to read the blurb about it, about where you want to use them from. But basically it's because it's a full year. And so it's not going to be a perfect poll because it uses everyone's, it does it for more than, oh, freaking out here apparently.
So that it actually covers more than we covered.
Covers CHEM 120 and 121.
Okay.
Yeah. Otherwise, if you really want like a better resource, then you want to buy the online study guide from the ACS.
Yeah.
They also have practice problems too.
Thank you.
All right. So it looks like what you guys want to do is the worksheet. So that's not a problem. So the reason why I wanted to make this worksheet was I felt like this worksheet, sometimes where we struggle is on these multi-part problems and kind of tackling them and kind of moving them along. And because Chem 120 does stack on each other, right? So sometimes I feel like the multi-part questions does a better job of kind of using your time so that way you guys can solve some of those higher level problems while also showing what you guys know along the way, right? So even if you don't know how to do a theoretical yield problem, you can still get some points for showing me what you can do, right? That you can do the complete ionic, you can do the net ionic, things along those lines, right? And so that's kind of why they're set up this way. So it's to save you time. It's kind of the idea behind it. Now, an exact copy of a question from a quiz or an exam is most likely not going to be on your final. A similar question to a quiz or an exam may be on your final, right? And so that is something to look at. What I would say instead is your quizzes and your exams are a good way to judge what kind of topics will be on your final, right? So quizzes are very specific. They cover just a couple of chapters at a time, right? Exams kind of take your bigger concepts from across many of those topics and many of those chapters and tries to tie that into one type of problem. And your final is basically trying to take all of the biggest topics from all of the chapters and tie that into one exam, right? So if you wanted to think about it, then all of your homework problems would kind of give you a largest range, but it also has a lot of information. Then your quizzes would be like that sampling of those, and your exams are a sampling of your quizzes, and then your final exam is going to be a sampling of your exams, right? And so that's kind of a way to process through to see what concepts or what topics are very important to know. Okay.
So Professor Lau, are we just going over the practice exam right now? Like just
so this is not a practice exam. So this is just two problems.
Questions.
Yeah. So this is just two problems. And so I'm going to read this for you guys. Then we're going to let you guys go and you guys can get started with this. So we're going to do like a breakout room so that way you guys can split that up. And then I'll check in with you guys. Then I'll pull you guys back in and we'll talk a little bit more about it. And then we'll kind of move on. Okay. So we're going to just work on this one problem. You guys can get your own copy of this problem. It's in the ACS exam review page. So from our Canvas link, right? And so this problem is that we have 350 milliliters of 1.789 molarity potassium chromate, and is poured into 725 gram solution of 5 mass percent cobalt-3 chloride. A precipitate appears at the bottom. If the reaction has 85.3% yield, how many grams of precipitate would be formed through this reaction? right? And so down below, it's helping you go through a couple of those steps, right? It's asking us to do a complete ionic reaction. It's asking us to do a net ionic. Then we're going to clarify those spectators. After that, it asks us, well, which one is our limiting? What would our theoretical yield be? And then what is our actual yield? Right. The bonus to this one is going to be what type of chemical reaction is this? And so for this, when you read this kind of question, what do you want to do as you start to read through this kind of like a little bit longer question? What's a good test taking strategy to do as you guys read through this? All right.
Doing
Summarize or highlight, right? So as you go through, what pieces of information are important? So what do you guys think? What's one important piece of information there? We know that there's 350 milliliters, right? So that seems important. What else? And we know the concentration of it. All right. And so one thing that I do is I actually change my colors and my underlining for my two different solutions. So my yellow is going to be one of my solutions. And so I'm going to use blue for my next solution. So it's my 725 grams and my mass percent. Okay. And so then I also like to include any chemical formulas, or not chemical formula, any names, right? So potassium chromate is going to be important. Cobalt 3 chloride is going to be important. And then at the very end, we have a yield here. And if you wanted, you can also look at that very last question because it tells you what you're trying to do. How many grams of precipitate would be formed? Right? And so this is something that I can see more when you guys do in-person tests and I get your whole test, is I can see who's marking up their questions and who's not. And I would say that this is one of the things that we could definitely always benefit from because there's a lot of information in there. So at least pulling out the correct pieces of information is a good way to go. Right? Now, your very first step, whenever you guys get a problem like this, you have a chemical reaction that you guys are going to need to come up with. What's our first step that we have to do?
Recognizing the nomenclature.
All right, we have to change our names to our chemical formulas. We have to do that before we can balance the reaction. We have to do that before we can solve for number of moles or find molar mass. Is we have to change our chemical names to our chemical formula. Once you do that, then you guys can go ahead and set up your chemical reactions, and then you guys will be able to get through this first 3. Okay. So I'm going to break you guys into groups so you guys can kind of get started on that part. And so I'm going to give you about 5 to 10 minutes to kind of get through that first section. If you feel comfortable, then you guys can go ahead and keep moving on past that. I'll probably bring you guys back just to check in, and then we'll move on to the next part as well. But I'm going to break you guys into groups as you guys get started. Does anyone have any questions on this before I kind of get you guys going?
Professor Lau, is chapter 12 going to be on the exam?
Sorry, what was that?
Is it chapter 12 on solutions? Is that going to be on the exam? The final
Yes.
exam?
Yep. All right, so our exam goes chapter 1 through chapter 12.
Okay. Thank you.
All right. There you go.
Quick question about the like the ionic reactions. Do you have to indicate the states for these?
Have to indicate the states.
Okay.
You have to indicate your states for any chemical reaction.
All right. Yeah, it's good to know. Thank you.
That's how you determine the spectator ions.
It's helpful for determining the spectator ions, but it's just good practice. So even molecular equations, you should also indicate your states.
Fair enough.
So remember that for your ACS exam, you guys won't get your polyatomic ion list. You guys will get that for your final exam. I don't think that it is worth enough points for your ACS to go through and like force yourself to memorize it. There's probably more useful ways you can spend your time. I think that by now, a lot of the ones that they use, you're already kind of familiar with, right? Like if they talked about carbonate or nitrate, things like that. I feel like a lot of you are used to it. They also don't do as much nomenclature on the ACS. They provide you guys with a lot of the chemical formulas, just because it's a different style test, right? So I know some of you are nervous about that part. I wouldn't be overly concerned with trying to memorize all the polyatomic ions. If it was that important, I would have made you memorize them from the beginning. All right.
Thank you.
So we have K2CrO4. And so what should the chemical formula be for cobalt chloride?
COCl3.
COCl3. Very good. So that 3, right? That tells us the charge of the cobalt. Now, often I do see people write it like that as cobalt-3 chloride, right? You want to remember that that Roman numeral is telling you the charge. It also doesn't tell you how many chlorides there are. That happens because chloride is a 1 minus, and so we should be doing our crisscross, right? So COCl3 in order to balance those charges. So good. So for our complete ionic reaction, we're starting off with them, K2CrO4 plus COCl3. And then what state are these two compounds?
Aqueous.
Both of them should be aqueous, right? So I like to write my molecular equation first. It just gives me an idea about what's going on. And then I break it up into all of its ions, right? If you wanted, you could just jump right to the ions. That's totally fine. And so how do we find what precipitate or what new products we can make from this type of reaction? What do we need to do?
Should we do like a double replacement?
We can do it like a double replacement where we put down here our different ions. And then we can look at that part, right? So do two cations go together?
No.
No. And two anions don't go together. And so our new products could be something like KCl and CO2CrO4 3. Now, why do we need to put parentheses around the chromate?
Because it's a polyatomic ion.
Because it's a polyatomic ion. So that 3 is going to go both to that chromium and the oxygen inside. Right? So it's going to both. And so looking at your solubility rules, what do you guys know about these two products?
Potassium chloride is aqueous.
We know potassium chloride is aqueous because all things with potassium, sodium, and most lithiums are aqueous, right? What do you guys know about the second one? Cobalt chromate.
It's a solid.
It's a solid. It's going to be insoluble, right? And that's because we know our chromates are insoluble except if they have lithium, sodium, potassium inside, or ammonium. All right. So
for the ACS, we have to remember all the solubility rules, right?
you do need to remember the solubility rules for your ACS, but they also use primarily the ones that I've made you memorize as well.
Wait, which one did you make us remember?
The ones that are always. So the things that are always soluble, those are the ones, right? So nitrates, ammonium, potassium, and sodium. All right, so looking at this, if we want to turn this into a complete ionic, what do we need to do?
We should balance the equations, right?
So we should balance the equation, so that's a good thing to do. And so when we're looking at that, remember that you can balance them by listing your elements. So we have potassium, chromium, oxygen, cobalt, chlorine. On this side, we have potassium, chromium, oxygen, cobalt, chlorine. Right now we have 2 potassiums, 1 chromium, 4 oxygen, 1 cobalt, 3 chlorines, 1. We have 3 of these, 12 of these, 2, 1. And so what's a good one to balance first?
Well, why not just start with the potassium since it's in the beginning?
Sure, we can start with potassium. So this should become 2. That changes our chlorine to 2. Good. So now we know that these are locked together, right? If one changes, the other one has to change. What do you guys want to do next?
Let's go for that chromium. So
right.
that should be 3 chromiums on the reactants.
So we need 3 over here. So that becomes 3. This becomes 12. And this becomes 6. So if that one becomes 3, what else do we need to change?
We have to go back to the product side. So
Mhm.
now we have to change the potassium again to
Right.
6.
So now we have to update this one. So if that one went to 3, then this one has to come up to a 6.
6. And that means it's
So this
6
becomes
potassium
6.
and 6
This becomes
chlorine.
6. Yep. Good.
So potassium is good, chromium is good, oxygen is good. We're left with cobalt. So cobalt is times 2, so 2 cobalt
So we need 2 of them here.
cobalt
That
chloride.
changes this to 6. And so then those are all connected. And so are we balanced now? What do you guys
Yes,
think?
that looks balanced.
6, 3. Yep, that should be it.
All right.
3, 2,
So-
6, 1. 3, 2, 6, 1. Yeah.
Now, this is the nice part about doing it on the computer is now we can just go ahead and clear those out. It's harder to do on your guys' exams, which is why like you can always do this on scratch paper and then just bring over your completed ionic. That's one way to do it, right? Because you don't always have enough space in the box, especially if you're like me and write really big, right? So you can always do it on scratch paper and then just bring over your answer at the end if it makes more sense to you. So we have it balanced. What do we need to do next?
So then now we write out each individual ion, but we keep the polyatomic chromate as like a polyatomic.
So we leave that one together as one ion.
Right.
Okay, so that means that we should have this as 6 potassium plus aqueous. And how many chromates should we have?
Plus 3.
All right, we need 3 of them. Good. And then we should have 2 cobalts. And what's the charge of our cobalt?
+3.
Plus 3. Very good. And we should have 6 chlorines, right? That's because there's 2 molecules and each molecule has 3 chlorides already inside. All right, so that's the left side. That's our reactant side. What do we do on our product side? Do we break them all apart?
No.
No.
Who don't we break apart?
The solid.
Right? So is it only solids that we don't break apart? Or what's the rule?
And liquids.
And liquids? Anything else?
Well, if you have gas, but I don't think that's going to be in here.
All right. So solids, liquids, and gases, leave them together. If it's aqueous, break it apart. Right? And so this one just should stay together as CO2, CrO4, 3 as a solid. Okay. We can back that out a little bit. Now,
Professor Lau?
mm-hmm.
Now, I initially actually had it as 2 chlorine 3. Is that okay? Or do you prefer it to just have 6 chlorine ions?
So the difference between this and this is a big difference, right? Because this one here is saying that you have all 3 chlorines and they're stuck together as a molecule, and that whole molecule has only 1 minus 1 charge.
Ah, that's true.
Right? This one is saying that you have 3 individual chlorines, and each of those chlorines has a minus 1 charge. Right? So which one more accurately displays how we would find the chlorides? The one on the right or the one on the left?
Right.
The one on the right, right? And so this is why we want to get out of that habit, is because really we have 3 separate ions, not one ion with 3 chlorines attached to it.
But it would also be okay if it was chlorine 2, just for example, because chlorine can exist as a diatomic.
So, but this one wouldn't be an ion. So if you had chlorine 2, then it better be a gas.
Yeah, that's true.
Okay. So
Never mind.
really, when you have an ion, then you just want to keep it as it should show up as an ion.
Gotcha.
No problem. Okay, so good. So now we want to do our net ionic. So what's the difference between the complete ionic versus your net ionic?
Professor Lau, I have a quick question.
Mm-hmm.
The complete ionic, I know that the bottom reaction, you have to do that, yeah. But do you have to include both, or like
So
inside of
my-
that?
for the answer that I would be looking for, I would only be looking for the one in the blue.
So the top one, what is that one called again?
This one is called your molecular chemical reaction or your molecular equation.
Okay, thank you.
Right? So it's already balanced. It's all of them, but they're all as molecules. All right. So what do we need to remove for our net? What's the difference between our net and our complete?
We're just looking for the precipitation of the solid, which is the cobalt to chromate.
So we know that we need that, but what's the rule? What are we trying to remove for your net ionic to your spectator ions, right? And spectator ions, what's the definition of a spectator ion?
They stay the same, or like they remain in aqueous state and they're ions.
It shows up on both sides and it's the same, right? And so in this case, which ones are our spectator ions?
Potassium plus and chlorine.
Very good. And so you're right, then we're left over with anything else. And so then our spectator ions would be the K plus and that Cl minus. Now, hypothetically, let's say that this was 5 potassiums and this one was 6. And then we I don't know, stuck a potassium onto this. Would we want to include one of those K pluses? I guess, sorry, let me get this so it balances. right? So we have 6K plus on the left, we have 5 on the right. Should we include a K plus over here?
I would say yes, because in that case, it wouldn't just be spectating. It would like, it's part of the product.
Very good, right? And so even if some of them behave the same, you can only remove the ones that stayed the same. If one of those Ks became incorporated into your product, then we would leave it, right? So this potassium became incorporated into our new product here. That doesn't make any sense, but that's why we would keep it. Whereas most of the other potassium was just a spectator. So you could remove those extra ones, but we should leave behind the one that's involved in the product. Good. All right. So now that's just our setup. What is the question asking us to find?
How many grams?
How many grams of the precipitate, right? And so just so we can kind of come up with a strategy there, what do we need to do? What do we need to find first?
The grams of potassium chromate.
Right? So why do we need to know the grams of potassium chromate?
Well, that was the information that was given to us in the initial problem statement. So I'm guessing once you find that, you're able to do the mole-to-mole ratio from our balance equation above.
So our potassium chromate, did it show up as grams?
No, but it gave us the milliliters and molarity. So from that, I was going to see if we can get grams from that.
So one good thing to do, right, is you're on the right track. What we want to do is we want to take those moles of the potassium chromate, so that way we can turn that into moles of our precipitate. Right. And in order to turn those moles into grams. Now, do we always have to be in grams in order to get to moles? Or can we get to moles through something else?
No, not always, but like how you just said, you can just do from that mole thing, but couldn't you also do that from this part? Wouldn't you be able to do it from the mole-to-mole ratio from the balance equation above?
So we are going to do the mole-to-mole ratio, right? So this is still going to be the mole-to-mole ratio in order to make this transition, right? That's what that transition is the mole-to-mole, right? But to get to moles of K2CrO4, we don't have to go from grams of it, right? And that's because when we look at our problem isn't giving us grams. It's giving us molarity, right? And so what are the units for molarity?
It's like moles over liters, I think.
Moles over liters, right? And so we don't have to find the grams of it because we have the molarity. So as long as we find the moles of it, we'll be able to plug that in. Does that kind of make sense?
Just to clarify, that's actually moles of something over the liters of a solution. Isn't that correct?
Mm-hmm. So that's going to be the moles of the potassium chromate over liters of this solution.
So for me, I've always kind of got a bit confused of how do you exactly determine which is a solid, which is a solution.
So can you have molarity if you are not a solution?
Can you have molarity when it's not? Wait, what?
Can you have a molarity if you are not a solution? Right?
No.
And you can't, right? You always, molarity only makes sense if you're talking about a mixture of two things, right? So you always have to have something dissolved in something else, right? So when we talk about this molarity up here in our potassium chromate, we already know that this must be a solution. And we know it has to be a solution because it has a molarity for it. It can't just be solid potassium chromate. Okay.
So that's the, let's see, that's the 350 milliliters that goes on the bottom.
And that, so it wouldn't go on the bottom, right? But we would use that volume to get into the moles.
1.71.
Right? So we'll get to that in a second. So that's one thing. So you're right. We need to, if we go back to what we're trying to set up, if we're trying to get to grams of our precipitate, we need to find the moles of our potassium chromate. What else do we need to know?
Our liters.
So we will need to find our liters, right? But let's say that's one half of our problem is the potassium chromate. What is the other half of our problem?
I think it was similar to what Elijah mentioned. Like we know there's 1 mole of potassium chromate to 1 mole of cobalt chromate.
Yep. But is our precipitate only going to rely on the potassium chromate?
No, because
no,
it's
so
725 grams of the solution.
Right? Because there's also the cobalt chloride side. So you guys are right. So we also need to find how much cobalt chloride we have. Because what are we going to do when we have two reactants? What do we need to determine before we can figure out our yield?
Limiting reactants.
Limiting reactant. So all of this really boils down, all the steps that you guys have been working down to is we have to figure out who is our limiting reactant. Because once we know our limiting reactant, we'll be able to figure out how much we can make. Now, how you find that limiting reactant could have a lot of different steps, and those steps depend on how you're given that information, right? But at the end of the day, you want to take the information that we have and try to get it into the moles of your solute, so the moles of whatever you have inside that's reacting. So we're going to try to get that into moles of the potassium chromate, the moles of that cobalt-free chloride. Because once you have it as moles, then you can do moles of your reactant over your moles of your product. And then we can go from moles of our product to our grams of our product using its molar mass, right? So we have some steps lined up there. And so that's what we're having to do. Find our limiting reactant, and then once we have that, find our theoretical yield. All right? So I'm going to let you guys try that out in your breakout groups, and then I'll come by and I'll check in on you. So just what I would say with solutions is it's really important to think about your units, right? Because you're trying to get both of them to moles. So pay attention to what you have, right? Grams of what versus grams of what, and then how can you move those over into getting it towards your moles? Do you guys have any questions before I send you to the breakout rooms?
So could we do like if it's 5%, would that just be like 5 over 100 grams times the 725 grams times the molecular mass, and then times 2
So if
moles?
you have 725 grams of your solution, right? Your mass percent means that there's 5 grams of cobalt chloride over 100 grams of your solution, right? And so those would cancel out. And now you're in grams of cobalt trichloride. And so then you're trying to move those along to get it to your moles, and then moles to moles, and then moles back to grams. Your product. Or maybe it was group number 4.
What is the question?
How'd you guys convert your potassium chromate solution over to your product? Right, so you guys had 350 milliliters of potassium chromate solution, how did you turn that into your product?
Do you guys want to volunteer and speak, or do you want me to talk? Sorry, we actually didn't come to who was going to talk.
That's okay. You guys can take turns. Someone can give me the first step. Next person can give me the next one.
Okay, so first we solve for our moles.
Okay. So how'd you solve for your moles?
Converting 350 mLs into liters. That's
Okay.
0.350 liters.
Mm-hmm.
Then we have let's see, we multiply.
I'll take over from here then. It's okay.
If you
So-
want.
It's okay. So 1.789, yep, moles of potassium chromate.
Right. And so that factor, what did that come from? What do we call this conversion factor?
That's the conversion of the molarity. Big M.
Molarity. Right. So this is the same as our molarity. We're just breaking it up into two parts. Good. All right. So now that we have a molarity.
We're actually not done though. Oh,
Mhm.
There's a little bit. So after that, we did the ratio of the cobalt chromate and potassium chromate. So 1 mole of cobalt chromate on top of 3 moles of potassium chromate.
Good.
Then you just distribute it from there.
All right. And so if we wanted to change that all the way into grams, does anyone have the molar mass of the gram of cobalt 3 chromate?
165.2913.
165.2913 grams.
Grams per mole.
Perfect.
Yep.
Did everyone else get that?
I actually just calculated it to the mole, and the mole is not in the mass.
That's okay. You can also calculate just to moles. That's fine. Limiting reactant, you can stop at moles, right? My thought process is if I'm going to do it, I'll rather just get it into grams because then by the end I'll have my answer because my answer wanted it in grams. But either one works. It's not a problem. Yeah. So we took that 350 divided by 1,000 times 1.789 divided by 3 times 165.2913. And so this gives us 34.49 grams.
Oh, wait. Oh, I'm sorry. I thought you said molecular weight of the cobalt chloride 3. The cobalt 2 chromate is actually 465.8475.
All right, that makes more sense. I was like, that seems too small, but it didn't seem like anyone else was worried. So I was going to trust you guys. All right, so let's divide that by 165.2913 times 465. So now I'm looking at 97.23. And so this value is telling us how much precipitate we could make if all the potassium chromate reacted. Okay. So my other room that I assigned you guys a task, you guys were supposed to take this 725 grams of solution and turn that into our precipitate from the cobalt chloride side. All right, so who wants to walk me through your guys' calculation?
I could do that.
Okay.
So first we have the grams of solutions, so we need to factor in the 5%. So that would be 5 grams over 100 grams, grams of cobalt 3 chloride over 100 gram solution. And then we multiply And then we can divide by the molecular mass of COCl3. So it would be 1 mole over 165.2913 grams. And then from there we have the moles of the product. Oh wait. And then we have to do 1 mole of the product over 2 moles of the COCl3. And then we multiply by the 465.8475.
All right. Good. So this becomes 725 times 5 divided by 100 divided by 165.2913 divided by 2 times 465.8475. And so what value did you guys get?
I got 51.2 or 51.24.
I realized that I multiplied it instead of dividing by the last one. Yep. So I have 51.08. Okay.
What's cobalt-chromate?
Yeah. So
yeah.
between these two, which one is our limiting reagent? Is it
So
our
since
cobalt chloride or is it our potassium chromate?
I would say it's the cobalt chloride since we need more of that.
So
it runs out first.
It runs out first, right? So it's the one that produced the smallest amount. Okay? And so that's going to be our cobalt chloride
Wait, Professor
limiting
Wong.
reagent. Mm-hmm.
Wait, actually, let me ask this question to Chris. How did you get your molar mass as 165.29?
So cobalt is 58.9 plus 3 times 35, 3 chlorines.
Checks out.
I actually calculated as for fluorine. That's why.
There we go.
You're actually correct. Sorry.
All right. So that's where we're kind of at, right? So now we have our cobalt chloride. And so now looking up at this, it asked us about if we have a yield of 85.3%. So how would that impact things for us?
So right now we're assuming at 100% yield, so we just multiply by 0.853.
Right? So right now we anticipated 51.08 grams, and that would be at 100%. So our percent yield is always your actual divided by your theoretical times 100%. And so you're right that right now this one is saying 85.3 is our actual, which is what we want, divided by this 51.08 grams. So we just need to solve for our actual, which is that 85.3 divided by 100, and multiply that by 51.08. So our actual yield becomes 43.57 grams. Now, does it make sense that we made less than we thought we were going to make? Does that line up well with our percent yield of 85.3%?
Yes.
Right. So that one does line up well for us. Okay. And so what kind of reaction would you say that this is?
Uh, precipitation reaction or double replacement.
A
I'm
double
not really sure.
replacement.
So this one would be normally considered a double replacement reaction, but you could also call it a precipitation reaction.
But are those like two different things? Like just because it's double replacement doesn't mean it's precipitation?
So just because it's double replacement doesn't mean it's precipitation, right? So
Sure.
if you had made a gas instead, that wouldn't be a precipitation, right? So like when you react baking soda and vinegar, it's a double replacement reaction, but it's not a precipitation because you make CO2 as a gas,
Okay, got it. Thank you.
right? So they don't always mean the same thing. You can also have a precipitation without a double replacement, right? You could do a single replacement precipitation. That also works as well, right? So there's just different ways to classify things. So there's a lot of different options there. Did you guys have any questions on this style question?
Yeah, so either or in the type of reaction will be okay, or you want us to write both?
So as long you could give me, if it was this open-ended for your like question, you guys could give me a whole bunch of different kinds of chemical reactions, right? You could say this was a double replacement. You could say it was a precipitation. As long as your reaction is correct, I would accept that definition, right? If I gave you options, then you would have to select all that apply or the correct ones from those options, right? So if you told me that this was an acid-base reaction, then you wouldn't get points for that. But if you told me that this was a precipitation reaction, then that would be okay.
Okay.
Yeah.
What about,
So
like,
it's
the
like all of the ones that apply. What was that?
But what about a neutralization reaction? Would this also count as that?
So why would it count as a neutralization reaction?
Oh wait. Oh, you know what? Maybe not actually, because isn't it that neutralization reaction like cancels charges on ions?
So neutralization reactions are specific. Normally, you're talking about them in terms of acid and base because you're canceling out you're canceling out the protons and the hydroxides, and so
Okay.
that's normally what neutralization stands for.
Yeah,
Sometimes
'cause
you do see it when they talk about charges, but it's not as common.
Yeah, because I think I get kind of confused like when to call something like a neutralization or like an acid base or wait, is neutralization basically just another name for an acid base reaction?
Generally, yes.
Okay. So
Yeah.
this would like most specifically be like a precipitation or like maybe double.
A double replacement or a precipitation would be your best ones that you guys know, right?
Okay.
So the big four that you guys know is synthesis or combustion or combination. You guys have decomposition, single replacement, double replacement, right? So those are like the four basic ones. From there, you guys also have acid base. You have, so I guess it's called an acid base neutralization. Combustion is a very common one, though I generally don't like to use combustion because it can get a little bit messy about what people count for it. But combustion reactions are very common, right? So it's something to know about as a keyword. And you guys also have oxidation reduction.
Dr. Lau,
Mm-hmm.
would dissociation fall under decomposition?
So dissociation right? You could classify it as decomposition because you're breaking up into more products than you have reactants, so that would be okay. Though generally you normally just say that this is a dissociation reaction, right?
For sure.
So it does count as a decomposition, but if you wanted to be more specific, you normally hear it called as a dissociation reaction.
Got it.
Mm-hmm. Okay. Any other questions for something like this?
Yeah. So I think like for the part with the theoretical and the actual year, like the values, I got something like very close, but it had like I guess like 3 sig figs instead of 4, and then it was like off by like 0.1 kind of something. So like on an actual exam, like how much would that matter? I guess if like you were
So
off by
that's
like
a good question. So what it comes down to is we need to go back to our first problem. And so how many significant figures should our answer have? And so this one here has 3 sig figs.
yeah, it'd be
This
3
one is
max,
4,
right?
3, 3, and this one is actually the culprit. And so that one's just a poorly written problem. I should actually change that because our answer should really just have 1 sig fig. And if you fit within that 1 sig fig, then you would have been fine, right? Most problems I try to write to have at least 3. And so then I look for some variability, right? So it depends on what happened, right? Did you round early on and that's why yours is a little bit different? And so then I would probably accept that. So being 0.1 off out of an answer like this, 51. So if you had 51.1 instead of 51.08, that's probably going to be fine, right? Or if you had 51.0 instead of 51.1.
Yeah, I had
Only there's like
51.2.
Yeah. And so normally for that, it's about where the variation occurred. The bigger problem is if you use something like instead of 165.29, if you only use 165, and that's why you started to veer off, or if you were using something like, trying to think of where, like let's say that instead of 97.23, you just were taking 97, so you like cut your number early, then that's when you can start to divvy up more than where what would be in the answer key, right? So a lot of times what happens is I try to do it without rounding, and then I try to do it if you rounded correctly, and then I try to do it if you rounded like 1 step too soon, and that's how I get my brackets of what range I'm accepting.
So there is kind of like an acceptable range.
So there is an acceptable range of what I'm looking for between them. One way to kind of see that is if you go to your grade scope, you can see what my brackets are for a lot of my answers about what range I'm looking for your final answers to be in. Very good. Any other questions on that part? So we have another question. This one is about gases. And so it says a sample of oxygen is collected in a rigid 3-liter container. It is captured at a temperature of 23.0 degrees Celsius and measured a pressure of 745 millimeters of mercury. Nitrogen is then added to the container until a pressure of 2.50 atmospheres is reached at a temperature of 38.2 degrees Celsius. What is the mole percent of oxygen in this mixture? Okay. So we should mark this up. We have our oxygen in the 3-liter container at 1 temperature and 1 pressure. We then have nitrogen being added to that. It's got a different pressure and a different temperature. So it's asking us for our mole percent. And so what is the definition of a mole percent?
We're looking for number of moles of oxygen over total number of moles inside the container.
Very good. So we're looking for moles of oxygen over total number of moles. And because it's a percent, then we're going to multiply this by 100%.
Right.
Good. All right. And so I'm going to give you guys some time to kind of work on this. And so I've given you some help here, Right? Now, there's a lot of different ways that you can solve this. Right? And so one approach is just to find the moles of oxygen before any nitrogen was added. The second one is then to figure out how many moles of gas there was inside that container, and then solve your mole percent that way. If you finish early, then you guys can work on to that second part, which is, would this sample of oxygen have enough to react with hydrogen gas to form water? And so that can be your backup one. So if you finish early. There's other ways to do this. You can also do it just by your pressures to figure out how much nitrogen there was added and then go from there. But either one is going to be fine.
So does this one involve like the ideal gas law as well as Dalton's law?
I was just about to ask that.
So what is the ideal gas law?
PV equals nRT.
So generally speaking, if you have a pressure and a volume and a temperature given and it's asking for moles, ideal gas law is pretty safe to assume, right?
For sure.
The only time that it wouldn't be is if you're not a gas, right? Or if you're at some extreme, right? So if we had like really, really high pressures and really, really low temperatures, right? So like that would be something more like we're at like 600 ATMs, 700 ATMs, right? Then the ideal gas law becomes a little funky, and then we need to be thinking about like, should we be making modifications to it, right? Should we be using the real gas law? But otherwise, if it's under normal conditions, PV equals nRT is going to be fine for what we're doing. Okay. Now, what's Dalton's law?
The total pressure is equal to, I guess, the sum of its parts.
And so do you have multiple gases in there?
I believe so, yes. We have the oxygen gas and nitrogen gas.
And so if you have multiple gases, then Dalton's law could always be in play, right? So Dalton's law is a good thing to have, and it's always useful if you have more than one gas. Right? Now, you might not exactly need it for this one, but it could be a way to get to what you're looking for. So that's not a possibility. Okay. Any other questions? Now for your exam, just this first part, so not including the bonus part, I would assume that a question like this would take you guys about 10 minutes. So I'm going to give you guys 10 minutes to work on this, and then we're going to come back at 5:15, and then we'll solve it together. All right, good luck. Did you have a question, Tiffany?
I guess just like writing out the ideal gas law, or like the gas. What am I thinking of? The gas equation. Yeah, that one.
All right, so it's always good to write it out, right? We have that. We also want to change it to what we're solving for. So N is equal to PV over RT. For some reason, this one is the one that people get mixed up the most on, because we often see RT over PV, right? So just be careful with that. Now,
I actually set it up as so one side is oxygen and the other side is nitrogen plus the oxygen. So it's PV over RT equals PV over RT, but it's one is the before.
So if you do PV over RT, right? So like one scenario versus the other scenario, what are you setting equal to each other?
Well, we're trying to look for the mole.
All right. So are your moles from here equal to your moles from there?
No, in that case.
No, right? And so you want to be careful with that because you can do a one where you set up a combined gas law, but you don't want to set it up as P1V, or you don't want to set them both equal to N, right? What you would set it up as is PV over NT is equal to PV equals NT, right? Because we know that their R's are the same value, right?
Oh, okay.
And so I'll solve it that way second. We'll do the first one in the simple way, and then we can do the second one, okay? So now that we have it here, we have our equation. What's another good thing to start with? So with gases especially, right, we have all of these different units that we can get them as. So what do we want to do to all of these units?
We want to make sure it's ATM, kelvins, and liters.
ATM, kelvins, moles, and liters, right? So if we can get them over there, that's what we would like to do, right? And so we can change our temperature here, this 38.2. That becomes 311. Three point 296. And our millimeters of mercury becomes 0.98026 ATM. Okay. And so if we want the moles of oxygen, then we only need to plug in for this one. Okay. So we can take our moles of oxygen is going to be our pressure. Times our volume, our temperature. And then what is our R value?
0.08206.
And so on your exam, where do you get that from?
It's on our equation sheet.
It's on your equation sheet, right? So if it's not listed in your problem, you guys can always get it through your equation sheet. And so how many moles of gas did you guys end up with?
So we got 0.121 moles of O2 gas.
And if we were worried about significant figures, how many significant figures would we want to record this out to?
3.
3, right? So you're right, 0.121 moles of O2. All right, good. And so now for the second part, we need to figure out the total moles of gas in the container. Okay, now I'm just going to do that up here just so that way we can see both parts. And so this time it's still the same equation, but we were using a different pressure. The same volume because it's still the same container. And our Kelvin, 311.35 Kelvin. And so one way to check is make sure that your units cancel, right? We have our atmospheres canceling out, our liters canceling a K. So we are getting moles, which is what we're looking for. And so we get 0.29354 moles. And that's moles of what?
Total gas in the container.
Right? So that's going to be moles of nitrogen plus oxygen, right? And if we look at the wording of the question, it's because that nitrogen is just added. And so what this found was our P total, our total pressure. So when we're looking for our mass percent, or sorry, our mole percent, we can take that moles of O2. We can divide that by 0.294 moles of N2 plus O2. We multiply that by 100% and we get our answer there. And so what mass percent, or what mole percent did you guys end up with?
I think our group got 41.2%.
41.2. Does everyone agree with that?
Yeah, that's what I got.
Good. Yeah. And that's what I got too. Right. And so that's what we're trying to do with that one. Now, if you had wanted to, you could have set up that combined gas law. So PV over NT is equal to PV over NT. Right? And so this would be our pressure of our O2, moles of our O2. This is going to be pressure total, moles total. And so what we're trying to do is arrange that so that we can get NO2 over N total. All right. So I would take this N here, I'm trying to move that up over here, and then I'm trying to take all of this and move that over. So I would have PO2 divided by the total pressure, volume divided by the volume, temperature of our total divided by the temperature of the O2, and that's going to give me my moles of my O2 over our total. So it is a way where you can do the one equation and kind of solve everything. It's also nice because you can also get rid of this volume because those cancel. And so you ended up with something that looks like 0.98026 atmospheres, 2.50 atmospheres, 311.35 Kelvin, 296.15 Kelvin. And we're still end up in that same value. Right? And so that's the power of the combined gas law, is you can also use that as well. Right? So there are many ways to solve gas problems, especially because there's a lot of different variety that you can do. So there's not really a wrong way to do it. There's just a different way, right? So as long as you get to the right answers, then that's also okay. All right. Did you guys have any questions on that?
I think the combined gas law would be really useful for the ACS, where we kind of have to like solve those kind of quickly.
So combined gas law is great for comparisons, right? Because you're right, sometimes you don't even have to do the math. You can just look at the ratio and you can tell, oh, that one's bigger than that other one by a lot, and you can see who's got more, right? So it can be really useful for those type of things. That's totally true. Good. So we've run out of time, but by next Wednesday, right? So what we start off with on Wednesday will be this one here, right? We start off with this on Wednesday, and then we'll talk about your online lab, and we'll take some more problem solving stuff, okay? So that's what we'll work on for Wednesday. Now, reminders, right? I'm trying to get over to our page here. That was today's review session up here. We do have our final exam review session on Wednesday, right? So we'll start off with finishing up this worksheet. We'll take some more questions, and then we will also cover your online lab. So if you can by Wednesday, you want to try to work on some of those problems. Right? You want to run this simulation, right? So at least make sure that it runs on your computer. If it doesn't run on your computer, then let me know, right? So when we show up on Wednesday, if it doesn't run on your computer, then we'll collect all of the data so you can do that experiment, right? If it runs on your computer, we'll have more time to take questions for your finals.
So do we have to run this on like Mozilla or something? Because I tried to run it earlier and or maybe do I just have to install Adobe Flash or something like
So
that?
you can run it on Chrome or Edge or Mozilla as long as you enable Flash, right? So you can run it on Chrome. You just have to go through your settings to enable the Flash or allow Flash to run for your computer.
Okay.
Yeah, right. And then if you want, what you can do is turn it on for like your incognito mode, and then that way you can turn it off when you're doing your normal browsing for everything else. So you do want to just take a stab at it. It's not a problem if it won't run on your computer. That's not an issue. We can collect all the data on Wednesday, right? That's totally fine. Once you guys have that going, then you do have your quiz for this week. There will be some time on Wednesday. We'll end early so that way you guys will be able to take your quiz. And then this lab that we're working on Wednesday, it's going to be due on Friday. So you just want to make sure that you guys kind of get that all moving along. It's the last lab. After that, you guys will be done. I'm just trying to get it turned in a little bit earlier so that way I can get everything graded and start to do dropping your lowest quiz, dropping your lowest lab next week, so you guys know where you stand. Okay. Any final questions from you guys? Okay, keep up the good work. We're so very close to the end. If you have any questions, I do have office hours tomorrow and on Wednesday. Otherwise, you guys have a great night. Thanks for coming.